right, let's get started. Share. Okay. All right, so we're all here, and hope everybody's doing well. My plan for today is to finish up this little section on series, and then we'll do a bit of a breakout at the end. If for some reason there's extra time, we might start on complex analysis a bit early, but it's Friday of the first week, so I'm all for taking a nap. So, all right, so we last left off, I just want to make sure that I have my lettering F, G, yes. We last left off with our expansions, and where this was leading to is a couple of different applications. The first of which is just identifying power series. And then what we can ultimately do with them. And of course, I keep saying this, but this is something that we've seen before, but we're just going to be a little bit more mathematically rigorous about this. So we'll start with a straightforward definition. Rather than just any old series that we've been talking about and series of functions, this is a series in which we can write successive terms as an increasingly high order polynomial. And essentially down to the total sum from n equals 0 to infinity of a sub n x to the n. So this is in some ways not that much different from what we've seen before. What's important now is how we use this. And in order to know when it's appropriate to use this or how we can use this is defining convergence. In this case, especially since eventually we're going to be talking about complex numbers and complex functions, we want to define or at least find a radius or interval of convergence. And while there are several ways of doing this, the most straightforward way of doing this is by essentially a comparison test. So we'll let the limit as n goes to infinity of one of these coefficients for n plus 1 over the previous coefficient for n be equal to r to the minus 1. That's our radius, or the inverse of our radius. Then the series converges for minus r between x equal to minus r and r. Now, that defines the region. If we want to know whether power series converges on the endpoints, we have to test those separately. So as an example, let's consider, let's see, I've got a couple of examples. Let's look at this one. Minus 1 to the n plus 1 times x to the n over n, which is actually a series that we've seen already. So it's kind of an alternating series. We know from this that a sub n is equal to minus 1 to the n plus 1 over n. And if we want to know the region in which this power series converges, then we look at the ratio of a sub n plus 1 over a sub n. Again, we're looking at the absolute value because we're trying to find that radius, the region around which this series converges. So this is equal to minus 1 n plus 2 over n plus 1 times n over minus 1 to n plus 1 absolute value. And so that's equal to the absolute value of n over n plus 1. So in the limit, we have n over n plus 1 goes to 1, so r is equal to 1. So, I mean, that kind of makes sense. This power series will be convergent on this region, then we need to check the endpoints. So if we look at the two endpoints, so what this means is that the power series converges on this region, but we haven't tested minus 1 and 1 separately. So if we look at x equals 1, what kind of series do we have? What does that look like?
Harmonic.
Right, in fact, it looks like the alternating harmonic series, which means that converges, right? Remember, the harmonic series doesn't converge, and in fact, when x is equal to minus 1, we get the harmonic series itself, and that diverges. So the region in which this power series would converge is convergent for values greater than minus 1 and less than or equal to 1. And I think you might have maybe one problem on the homework looking at the region of convergence. If it's not this homework, it's a later homework when we look at the circle of convergence for complex numbers. Okay. So I think it's pretty straightforward. Again, it's kind of a comparison test, and the last thing I'll say about this, we'll use it in a bit, are some of the properties. Of power series, namely uniform convergence. Basically, if it's convergent, if the series is convergent, then it's uniformly convergent in this region R. Basically, also, if we have continuous functions, then we can assume that we can define integrals and derivatives, again, on this region R. And as usual, there's a uniqueness theorem too, which we'll get to later when we talk about solutions of differential equations. That's essentially it. And we'll also come back to this when we look at ways of solving differential equations using a power series, the method of Frobenius. Have people seen the method of Frobenius? Have I asked that before? No? Okay. We'll see that in maybe 3 or 4 weeks. Okay. All right. I think people are done writing. If not, just let me know. Okay. All right. Next, and you do have at least one, maybe one problem on this in your homework, and that is one of the reasons why we're doing this, and that is integration. This may not seem all that useful these days with things like Wolfram, but you never know when you might be stuck without internet access in a quarantine house. So how can we use these expansions to evaluate integrals? Well, there are a number of ways, and I got a couple straightforward examples, one that's pretty similar to one that you have on the homework, and another that is just sort of interesting historically. And the idea here is that you take whatever functional expression you have that you can, as long as you can write it as a series that's appropriate on the interval, you can integrate it. I guess I should say examples up here. And then I guess this is example 1. Doesn't really matter. Let's define the integral I as the integral from 0 to 1 of dx over x times the natural log of 1 plus x over 1 minus x. So without, short of looking this up on an integral table or doing this numerically, this actually is pretty straightforward to do if you use the expansions. In particular, we've already seen earlier this week that we have an expansion, right? So we have an expansion for the natural log of 1 plus x as long as x is between -1 and 1, right? Which certainly fits the bill for this interval. So if we take this interval, give you some room here, I is equal to the integral from 0 to 1 of dx, and then we have x to -1, and then we can expand out the natural logarithm of x of ln of 1 plus x, so that's x minus x squared over 2. This is something we did near the end of last time, x cubed over 3 minus x4 over 4. And then minus x squared over 2 minus x cubed over 3 minus x fourth over 4, and so on. Okay, so we're just taking those two expansions, and it should be clear that the even terms are all going to cancel each other out in this expression. Okay, where's my pen? And so that ends up, when you do the evaluation, so this just is a polynomial, right? So if we skip ahead to evaluating this from 0 to 1 of the odd terms, we end up with 2 times 1 plus 1 over 3 squared plus 1 over 5 squared plus so on. And we could leave it like this, but as we're going to see later on, so this is a perfectly fine answer. It does suggest a series. One of the things that kind of skipped over and then we'll come back to are special integrals. And in particular, there's an integral representation for the Riemann zeta function. My zetas are terrible, where zeta of x is equal to 1 over gamma of x. Remember, the gamma function is an integral expression for the factorial. And this is times the integral of t to the x minus 1 dt over e to the t minus 1. That's not, I mean, that's neither here nor there, but you can write out a series expression for this, namely, depending on what the value of the zeta function is, that is, and you'll encounter zeta functions in quantum. You'll especially encounter it in combinatorics, but essentially, I think where you would most see this is in quantum. You can write 1 over 2 squared zeta of 2 is equal to 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared. And so zeta of 2 minus 1/4 of zeta of 2 actually turns out to be our integral that we started with. So if we evaluate, basically we have 3/4, but we have another factor of 2, our interval becomes 3/2 of the zeta function, zeta of 2. I mean, that's just sort of a straightforward way of expanding it. And again, getting to that first point is the most important part. For physics applications, it's when you understand when the zeta function is important that kicks in. Okay.
I have a question.
Sure.
Zeta of 2 minus 1/4, zeta of 2, how did you get the 3/2?
Because this is 3/4. Oops. Sorry. We got a 3/4 over here, but our integral expression up here has another 2.
Oh, okay. Thanks.
Yep, no problem. All right. Thumbs up? We good? I know there's a lot of writing. Okay. Another example, and this is just more of a utilitarian example. It's also very similar to something you have in your homework. I think number 1.10.3. So you can do the integral from 0 to infinity. Ask what is the value of 1 over sinh of x. Okay. Now, this may or may not be a divergent interval. Okay. You, I think, in your homework are asked hyperbolic cosine, 1 over hyperbolic cosine. That is a convergent interval. So we can write this as 0 to infinity dx. And then one thing that I haven't covered yet, but I think you've probably seen, and it's in the book in I think it's in 1.9. We'll come back to it next week. Is the exponential expression for hyperbolic functions? Have people seen that? Okay. Okay. You know the exponential forms for sine and cosine, right? So e to the x plus e to the minus, or I e to the minus x over 2, and things like that. For hyperbolic sine, we can write that as e to the x minus e to the minus x over 2. But we're taking the reciprocal of that. Okay, so that's just one way of representing a hyperbolic sine. So the way that we can go about this, well, all right, let's write this out so it's a little more obvious. Just one more step here. So this is, in fact, we'll put the 2 out of here, dx over e to the x minus e to the minus x. All right. What's a way we can proceed here?
Power series of e to the x.
We could do power series of e to the x, but here this is actually getting back to another kind of expansion, right? So if we have something that's like x and 1 over x, one thing that we can do, I mean, your answer is not wrong, Nick, except that it would provide like power series in the denominator, right? Which makes things a little more complicated. So if instead what we do is write this interval or the argument by factoring out e to the x. So now we have 1 over e to the x times 1 minus e to the minus 2x to the minus 1. Now what might we do?
Binomial expansion.
Right, now we use the binomial expansion. Now we can get things that are term by term in the numerator. So this can be written as 2 times the integral from 0 to infinity of dx, 1 over ex. And then the binomial terms e to the minus 2x plus e to the minus 3x, and so on. And then I'll leave that to you to, do I have that right? Yeah. To do the derivative or to do the integral and then evaluate it at the ends. This actually is not as nice as the hyperbolic cosine. Hyperbolic cosine term should get you to a actually convergent number. So in equation 1.6 in the homework, this is similar to 1.10.3. That is 1 over cosh x. Okay. Okay, and then finally, well, not finally, just one more simple example, and then I want to get into a little more complicated example. The integral from 0 to infinity of dx over 1 plus e to the ax. That, again, now that we've seen this, that argues for another straightforward binomial expansion, e to the minus ax minus e to the minus 2ax plus e to the minus 3ax, and so on. This will give us a series 1, when we evaluate this, as 1 over a minus 2 over a plus, oops, oh, I don't know, hang on. All right, got ahead of myself. 1 over 2a, 1 over 3a, minus, plus, and so on. But you should recognize this as, again, the expression for log, natural log of 1 plus x. In this case, where x is equal to 1. So this ends up being 1 over a times log of 2. All right. Sorry if that was a bit messy. Right before you showed up, I spilled coffee all over my notes. So I'm doing the best I can to read this shit. So. All right, stick a break, bring out your hands. If you got questions, ask them. Let's see. Now, I had planned a really long section on this next topic, but what I'm going to do is sort of skim over it, and then I'll make a 5-minute YouTube video on where all of this comes from, and that's the elliptic integrals. How many people have seen elliptic integrals? Dennis, again with the face.
Don't ask me to explain them, please. I've just seen them.
All right, so I'm just going to go brush over it very quickly, and then I'll go over the full development. But it's, again, another example of how we can use expansions. So, and where this comes in is that it's an integral that is designed expressly to solve something like the pendulum problem. So where we have typically taken our usual small angle approximation, or even developed it more fully and then did a numerical solution in, say, computational mechanics. The elliptical integrals were originally designed to integrate and give the arc length along an ellipse. And in fact, our good friend Euler is responsible for this. The general definition is a function f of x is equal to the integral from some point c, function of x, and then a parameterized function r t p of t dt, where r is a rational function of two arguments and p is the square root of some polynomial series. The what's sometimes called incomplete form of this, incomplete, is sometimes written function of phi, which might be an angle, and alpha, which is a sort of a modular angle. Sometimes it describes the eccentricity. So it's essentially a parameter, is the integral from 0 to phi of d theta over the square root of 1 minus sine squared alpha sine squared theta. So this is something that that you can use to basically evaluate the length along an ellipse. There are other forms of this too. You can write this in terms of parameter x and m more generally, so that this is the integral from 0 to x of 1 minus t squared times 1 minus mt squared all to the minus 1/2 dt for m between 0 and 1. The reason why I bring this up is that this is all suggesting some kind of series expansion. And like I said, we can use these to do the arc length. What I mentioned at the top of this section is the pendulum problem. Okay, so this is kind of an opaque but kind of interesting view of how we do the pendulum problem. So if we start with our usual setup, of a pendulum, and a starting angle alpha, an active angle or instantaneous angle theta, and a mass m. We can start with a Lagrangian approach, which I think most of you have seen, at least in terms of Poief. But we defined the kinetic energy, 1/2 mv squared, as 1/2 m L theta dot squared, and the potential energy as minus mgl cosine theta, so that we're defining our two variables as theta, well, our main variables theta. Then our Lagrangian is t minus v, right? So that's 1/2 ml squared theta dot squared plus mgl cosine theta. And then our equation of motion comes from ddt of ml squared theta dot plus mgl sine theta is equal to 0. And if we want to write this in terms of thetas and alphas, that is, we're going to consider a swing of amplitude such that the theta dot is equal to 0 when theta is equal to alpha. So theta dot is equal to 0 when theta is equal to alpha. That's our initial position. We can eventually write that theta dot squared is equal to 2g over L times cosine theta minus cosine of alpha. But this is, of course, d theta dt, right? So then we have this interval. And then our job is to integrate that. And that's not necessarily obvious, but we can get, for example, we're integrating from 0 to say alpha d theta times this square root cosine theta minus cosine alpha. That equals 2gl square root from 0 to t. And so tg over L t, where t is equal to, right now, basically 1/4 of a period. Where does this all get us? Again, I'm going to skip over a bunch of stuff. Then a miracle happens. It's not just you guys who do this. But essentially what we're doing is defining a bunch of parameters. In this case, we could define cosine theta minus cosine alpha as equal to a parameter, or define it in terms of a parameter k, such that 1 minus 2k squared sine squared phi minus 1 plus 2k squared is equal to 2k squared times 1 minus sine squared phi. And here k is defined as sine of half that starting angle. What is this bias? Well, eventually we can write, remember the period that we're solving for, we're basically solving for 1/4 of the swing. T can be written as, on one side, putting everything on the other side, 4 times the square root of L over G times the integral from 0 to pi halves of d phi over the square root of 1 minus sine squared alpha over 2, extend this over, times sine squared phi. All of this is essentially k times sine squared of alpha 2. And like I said, this is kind of opaque. But now we're in a position to solve this if we let x be equal to this, an expression, basically k squared and sine squared phi, and expand the integrand. So the main lesson here that I want you to take from this is that you could take this complicated expression for something that's swinging on an ellipse, and because we know how to expand on the appropriate interval, right, a series, we can write that t is equal to 4 times the square root of L over G, the integral from 0 to pi halves of d phi, times 1 plus 1/2 k squared sine squared phi plus 3/8 k to the 4th sine to the 4th phi, and so on. Once we have that, we have an infinite series that we can integrate term by term. We're basically integrating a series that's the terms of each series is k to the 2n sine to the 2n phi. So once we recognize this and integrate term by term, we have that t is equal to 2 pi times L over G to the 1/2 times 1 plus 1/4 sine squared alpha over 2 plus 9/64 sine to the 4th alpha over 2. Remember, alpha is just a constant, and so on. And again, for alpha much less than 1, we get t approximately equal to 2 pi over the square root of L over G, which is what we expect. Okay. I don't expect this to be completely translucent the first time through. But again, I just wanted to show you some of the power of this, and I will go through the full derivation in a different video. Okay. Are there any questions about this, just the general concept? And I think your book does have a section on elliptic intervals. It might be in the first chapter. Okay. Okay. Last section of this first week is a section on asymptotic series. What are asymptotic series?
They do something interesting as they go to infinity.
Right. In essence, we make use of series that are essentially divergent, and they're asymptoting to something, but they're not converging, right? So we can make use of their properties at large values. Generally speaking, there are two types that we're interested in. I1 of x looks like this. Say the integral from x to infinity of e to the minus u f of u du, and I2 of x from 0, sorry, to infinity of e to the minus u f of u over x du. And our job is to recognize these and expand the functions. So we want to expand the f of u or f of u over x. What we want is an asymptotic expansion. That is an expansion of f of x that has the properties such that the limit as x goes to infinity of x to the n r to the n of x equals 0 for fixed n. Or x to the, as n goes to, nope, as n goes to infinity, sorry, x to the n or the n of x equals infinity for fixed x. I haven't defined what r sub n is. You can think of it as almost a remainder, where we're taking a power series and considering r sub n of x to be equal to x sub n times some f of x minus that partial sum of x. Right, where s sub n then is that partial sum of a power series. So s, let's say 0.5. S sub n is just equal to a naught plus a1 over x plus up to an over x to the n. So for power series R sub n, is x to the minus n minus 1, and our function that we're interested in, functions, will be the sum from 0 to infinity of a sub n x to the minus n. So that doesn't really give us a whole lot of insight at the moment, but we can consider an example. And one example, there are actually several. This is in, I think, section 10 or 11. And that is essentially the gamma function, or no, not exactly the gamma function. It's E1. So E1, let's see how I'm going to write this, is we can write as the integral from x to infinity of e to the minus u over u du. And the question is, how do we represent that? Well, we can represent this, excuse me, in terms of, well, I think the first thing that we want to do is integrate by parts and evaluate. So e to the minus x over x minus the integral x from x to infinity of e to the minus u, now u minus 2 du. If we do that again, that's e to the minus x over x minus e to the minus x over x squared plus 2 times the integral from x to infinity of e to the minus u to the minus 3 du. You can sort of see where we're going with this. We're trying to actually create an infinite series out of these intervals. So if we keep going, this will end up being e to the minus x over x minus e to the minus x over x squared plus minus, and so on to minus 1 to the n minus 1 times n minus 1 factorial over xn e to the minus x plus minus 1 to the n factorial times this last integral of e to the minus u to the minus 1 plus n du. Okay, so what we do with this then is separate out the series and the integral. So this is equal to e to the minus x times the sum from I equals 1 to n of minus 1. And I should have not used an I here. That might be a little confusing. That's not imaginary I. I minus 1 factorial over x to the I plus this integral from x to infinity of e to the minus u to the minus 1 plus n. Okay. The reason why this is important is that you can show this is divergent. So what do we do? Well, we can write e1 of x minus Sn of x is now just equal to that integral, right? This is S sub n. This is our partial sum of this series. Our R is essentially this integral, right? So that equals this thing right here. And so E sub, or E1, I guess I'm writing it E1, E1 of x minus S sub n of x is going to be less than or equal to n plus 1 factorial times the integral from x to infinity of e to the minus u to the minus n plus 2 du. What we can do here is do some substitution. So we're setting up when we can use, or how we can use this integral and how to represent it as a series. The rest of this, I don't want to spend too much time on it, is a substitution. If you let u be equal to v plus x, you could represent this integral as e to the minus u to the minus n plus 2 du, and eventually beat that into e to the minus x over xn plus 2, integral from 0 to infinity of e to the minus v, 1 plus v over x to the minus n plus 2 dv. I guess this should be, do that. And then the question where we finally get to all of this rigmarole, blah, is let x go big. In other words, what's the asymptotic expression of this function for arbitrarily large x? The integral from 0 to infinity of e minus v over 1 plus v over x, the n minus to the minus n plus 2 dv goes to the integral from 0 to infinity of e minus v dv, and that goes to the value of 1. In other words, this expression e1 minus Sn of x ends up looking like n plus 1 factorial e to the minus x over x to the n plus 2. So for large enough x, h.10 is a good approximation to our fundamental integral E1. Okay. So the utility of this is often we look at what happens when x is small, right? In an asymptotic series, we look at what happens when x is large, and use that as our approximation. And so it's kind of a nice, in terms of where we've gone in the last week, we've started with definitions of series, and then looked at how they behaved as approximations for small values, that is, taking a limited approach around a small space, and looked at how we can apply that, and then we ended with these expressions for when x is quite large, right? Including things like the elliptic integrals. In terms of asymptotic series, your book has several different examples of that as well. But this is the E1 integral is a pretty good, essentially gamma function. It's another good case. Any questions? Okay, so if there are no questions, which doesn't seem to be, I am going to try and do this without kicking everybody off. I would like to, let's see, manage my stuff, make breakout rooms here. And why can't I see, let's see. Oh, here we go. Manage participants. More. Breakout rooms. There we go. I'm going to do this. Let's see. Automatically create. Why do they? Oh, I see. All right. So cool. I can't see you because I've got too many screens here. I'm letting this do this automatically. You're going to be assigned to 2 persons per room. And what I want you to do is, again, reflect on what's the most important thing that we talked about this week, or the main idea. An example of that, not necessarily, in fact, hopefully not, something that we've actually talked about. And you can talk about things that are maybe a little confusing, either, however the class is run or the material. You don't need to share that when we get back. I'm going to give you about 5 minutes to talk about it in groups on your own, and then we'll come back. There'll be a link on the Moodle site for you to upload what you've done. Everybody understand that? Good. All right, let's do this. Open all rooms. All right, so I guess I gotta move you. Move. I guess I'm in your room. Nope. There. Awesome. Okay.
very conveniently, Ben and I got put in the same breakout room, but
Awesome.
so
Yank.
sorry.
Okay, well, I mean, all right, that's fine. All right, who wants to share?
I will.
Okay.
Nick and I were in our little breakout session together, and we thought the binomial expansion is pretty important because it keeps popping up all the time. And the physical example that we used, or sort of like a physical thing where it's used a lot, is with an E&M with like quadruple expansions.
Awesome, that's great. Anybody else? Yep, go ahead, Adrian.
Ali and I talked about, I guess the big idea is you can like use series to like make complicated things simpler, especially like with integrals. You can make a hard integral easier by just integrating the expansion. And one example we thought of was in thermal physics for, I guess, making the partition function look a little bit better. We use the geometric series.
Yep. That's great. Good. Couple more. Ennis, what did you guys talk about?
So at first we talked about we were both kind of interested in like the elliptic integrals and the treatment with the pendulum. An example that I thought of back summer of like 2 years ago, I was trying to write a program in Python that would track and calculate eccentricity based on just raw planetary data.
Mhm.
And the first thing I came across was like, all right, using elliptic integrals, and I read it and then I closed it. So that was my main physical experience with them until AdMath, which was more elliptic integrals.
Okay, cool. How about one more? Steven?
Yeah, Yuri and I came up with like a main idea that was pretty similar to what Adrian was saying, just that we can take these sort of extreme cases of really complicated forms of equations and especially integrals and simplify them, or at least get a really good approximation using series.
Okay, good. I hope this was a good first week. If not, please let me know. Please let me know how I can make this better. We're all sort of in this together, trying to find our way through all of this. And it's not just me. Make sure you contact all of us. We're trying to really make this as good a thing as possible. This is an okay first week. Okay. Okay. It's all right. Okay. So I guess I'll end and I'll make this available online, and then also open up where you can submit things on Moodle. Okay. Aww.
He says bye and thanks for teaching him so much stuff this week.
Awesome. All right. Well, you guys take care. Stay safe. Stay healthy. I'll see you on Monday.
Bye.
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 Bye, Willa.